Okay, everyone. We have a nice integral today here. It's sort of like a mixture between a Gaussian and inverse tangent. Well, the derivative of the inverse tangent, but you get the idea. So let's going to evaluate real quick here. So the first step is a little bit esoteric, or maybe even not used at all. So we're going to multiply both sides of the equation by e to the minus 1. So and because e to the minus 1 is a multiplicative constant, we can just put in the exponent inside of the integral. So, okay. And so now we can just factor out this negative here. Anytime you have the integral of the sort, the integral from a to b, f of g of x over g of x dx, you should probably think about the Feynman technique and probably consider it. Sometimes, well, a lot of the time it works out because Feynman's broken. So here's how it would go. You would let a new variable, let's say z of t equal to, go from a to b. You have f of z times g of x over g of x dx. Okay, now differentiate both sides of the equation with respect to t. What do you get? You get z prime of t equals, to go from a to b. Okay, so the g of x, you can bring that out due to the chain rule. It actually cancels out with the denominator. So this cancels out the new integral here. I shouldn't slash it through here. So then you just get, in the end, you'll get f prime of t times g of x dx, which is quite useful. We can apply this to this situation up here, and that's what I'm going to do. Now, time to... Okay, so we're going to let a new function with respect to a function of a, equal the integral from 0 to infinity, sorry about that, e to the minus a times x squared plus 1 over x squared plus 1 dx. Right, now, differentiate both sides of the equation with respect to a. Get f prime of a equals, okay, minus right there. So you have minus x squared plus 1 cancels out with the denominator, so that's nice. But now we have e to the minus a times x squared plus 1. So you can factor out the 1, the x squared part. So when you get e to the minus a here, the integral from 0 to infinity, e to the minus a x squared dx. Now this is actually very similar to a Gaussian. And this can be transformed into the Gaussian quite easily with a single u sub. So it'll go as follows. U equals square root of ax, right? Yeah, okay. Right? Yeah, okay. And du is going to equal square root of a dx. So then you get dx equals du divided by the square root of a. So that's going to transform this into a Gaussian, but we have to divide by the square root of a. So then you get minus e to the minus a times the square root of pi over 2 root a. And as any of you that didn't know, okay, if any of you were trapped under a rock or are neophytes to calculus, then the integral from 0 to infinity e to the minus x squared dx equals the square root of pi over 2. And this is known as the Gaussian integral. Sorry I didn't elaborate on this earlier, but... Okay, now. So this is equal to f prime of a. But to retrieve our original integral, we have to find f of 1. Just not f prime of 1, f of 1. So we're going to integrate both sides of the equation. What do we get? We get f of a equals minus the square root of pi over 2 times the integral of e to the minus a, and that's a to the minus 1/2 to the exponent rules, dA. And this is where is where people don't really enjoy this. I found this is actually a non-elementary function, which, sorry about that. But I mean, we get pi in the solution, so it's all right. Okay, so namely, the non-elementary function is called the upper incomplete gamma function. So minus, this integral is equal to minus gamma of 1/2 a. Now these negatives will cancel out, and then you have to add the constant integration. Sorry I didn't do that earlier, but okay. Now, the one thing precluding us from navigating our way to the solution is c right here, right? So we have to calculate what c is. That can be done fairly trivially. Now, okay, so we're going to let a go to infinity because, okay, this is actually equal to, if you recall, plus c, sorry. If you recall, this is actually equal to f of a. So we have to find, when a equals infinity, we're going to let a go to infinity so we can find c. Okay, so f of a is up here. So then you have e to the minus infinity times quantity x squared plus 1 in quantity. And that's actually equal to 0. So that's nice. Now we get the square root of pi over 2 times the incomplete gamma function of 1/2 and infinity. Now what's this? This is also 0, or, well, plus c equals 0. But this is also 0, the incomplete gamma function of anything and infinity, due to the incomplete gamma function definition, which is gamma of ax equals the integral from x to infinity e to the minus t times t to the a minus 1 dt. So if you plug in infinity for the x right here, you get infinity to infinity. Same limits, same upper and lower bounds of integration. Therefore, it goes to 0. And then we get c equals 0. Now we don't have to worry about c. Okay. So now how do we retrieve I? We know that I is equal to e to the minus x squared plus 1. So to regain I, we have to let a equal to 1, right? And then multiply by e. So we're going to let a equal 1, and we get square root of pi over 2 times gamma of 1/2 and 1 equals e to the minus 1 times I. Multiply both sides of the equation by e, and you get e times the square root of pi over 2 times the gamma of 1/2 and 1 equals I. However, this is not pretty due to this bastard right here, by my French. Now, I equals e times the square root of pi over 2 times, okay, if you type this into Wolfram Alpha, you'll find that gamma of 1/2 and 1 actually equals to square root of pi times 1 minus ERF of 1. Okay, so combine the square roots, and you get I is equal to e times pi over 2 times ERFK of 1. Where did I get ERFK? ERFK is actually equal to, ERFK of x is equal to 1 minus the error function of x, which is pretty weird, but yeah, that's it. That's a pretty yeah, that's a good place to stop, actually, so I'll stop.